Chapter 3, Conduction within a solid object, under the condition that it is one-dimensional and it is at a steady state. The solid object can be a wall or a fin. Topic 1. Conduction in a single wall. A wall is a vertical structure that encloses an area. In heat transfer, if the geometry is rectangular, it is defined as a plane wall. If the geometry is cylindrical, it is defined as tube wall or cylindrical wall. If the geometry is spherical, it is defined as spherical wall or spherical shell. A. Heat equations for single walls. For a plane wall, equation 1 represents the heat flow rate of conduction going through the thickness of the plane wall. The heat rate is determined by the temperature difference between T1 at left surface and T2 at right surface, divided by L, the thickness, over A, the surface area, and K, the thermal conductivity of plane wall. For a tube wall, equation 2 represents the heat flow rate of conduction going through the thickness of the tube wall. The heat rate is determined by the temperature difference between T1 at radius R1, T2 at radius R2, divided by the natural log of radius ratio over 2 pi L, the tube length, and K, the thermal conductivity of tube wall. For a spherical wall, equation 3 represents the heat flow rate of conduction going through the thickness of a spherical wall. The heat rate is determined by the temperature difference between T1 at radius R1 and T2 at radius R2, divided by the difference in 1 over R over 4 pi K, the thermal conductivity of spherical wall. Furthermore, we can introduce equation 4 to calculate the heat flux for the plane wall, which represents the heat flow at a specific point of area A. We can also introduce equation 5 to calculate heat rate per unit length for the tube wall, which represents the heat flow along the perimeter of the tube wall. We can also introduce equation 6 to calculate heat rate per unit volume for the spherical wall, which represents the heat flow at specific point within the spherical wall volume. Finally, all these equations are only valid under the condition that the system is steady, there is no energy generation within the wall, thermal conductivity K is constant, the conduction heat flow only occurs along the x direction or the r direction. Topic 2. Thermal resistance and thermal circuit. Analogy between electrical circuit and thermal circuit. First, physical setup. On the left, it is electrical loop. On the right, it is a thermal plane wall. We know that whenever there's a voltage difference, then there's a current. Similarly, whenever there's a temperature difference, then there's a heat flow. Second, we can define electrical thermal resistance R as the voltage difference dot V over the current I. Similarly, we can introduce a new variable, thermal resistance RT. R represents resistance, T represents thermal, which is defined as temperature difference delta T over the heat rate Q in the unit Kelvin or Celsius over watt. Third, we can draw the thermal circuit. In the electrical closed loop, this symbol represents switch, battery, resistance. They are connected by the straight line, and the circuit is labeled with V1, V2, R, I, with arrow to represent the direction. Similarly, we can draw our open thermal circuit. We start with empty dot to represent T1 surface, goes straight, then a zigzag. This symbol represents thermal resistance, then it goes straight line, then draw an empty or solid dot to represent temperature T2 surface, then it is labeled with RT, and heat rate, Q conduction, with the arrow to represent flow direction. Next, we're interested in relating the thermal resistance RT to the wall geometry parameters and heat transfer mode, so that we can calculate the thermal resistance value. How do we do that? This is the definition for the thermal resistance RT. We can switch these two variables to yield the definition for the heat rate, which is delta T over RT. Then we compare our heat equation with the definition of heat rate to come up with the calculation equation for RT, the thermal resistance. B. Math equations for thermal resistance RT. For a conduction in a plane wall, equation 1 represents the heat rate. Then we compare equation 1 with the definition or heat rate. We compare, this is the heat rate, this is the heat rate, this is the temperature difference, this is the temperature difference, this is the RT, so this is the RT, the thermal resistance for a plain wall. Similarly, for conduction in a tube wall, we can define this is a thermal resistance for a tube wall. Again, for conduction in a spherical wall, we can define this term, which is our thermal resistance for the spherical wall. We can do the similar comparison with convection to get the thermal resistance for the convection, and we do the similar comparison to get the thermal resistance for radiation. In this definition of RT thermal resistance, HR is radiation heat transfer coefficient. It is calculated from equation here. For your study convenience, an equation table for thermal resistance is made. As you can see, this is the definition for the thermal resistance RT, which is a temperature difference over heat rate Q in this unit. It then yields the RT for radiation, convection, plane conduction, cylindrical conduction, and spherical conduction. Second, we can define RT double prime, which is a temperature difference delta T over heat flux Q double prime in this unit. It then yields the RT double prime thermal resistance for radiation, convection, and plane wall conduction. Third, we can define thermal resistance RT single prime, which is a temperature difference delta T over heat rate per unit length Q single prime with this unit. It then yields RT prime for radiation, convection, plane wall conduction, cylindrical wall conduction. If we do a quick summary at this point, we covered topic 1. We introduced heat equations for different geometries so that you're able to apply those heat equations. In topic 2, we define thermal resistance, thermal circuit, and mathematical equations for thermal resistance so that you're able to draw the thermal circuit and calculate RT thermal resistance by selecting proper equation. Let's practice example 3-1. As shown in these two figures, a tube wall and a spherical wall. This tube wall has a length of 1 meter, and both have the following properties. As at R1, we have temperature T1 at 20 degrees. At R2, we have temperature at 10 degrees with K, the thermal conductivity of 10 watt per meter per Celsius. We need to draw the thermal circuit and find the thermal resistance RT and heat rate Q. Let's start with tube wall. Where do we start? to get unknown and draw thermal circuit. We need to identify the heat transfer mode. Since we have a temperature difference, then we have a conduction heat flow going through the thickness. Now we can draw the thermal circuit. We start with a high temperature at T1 using the empty dot. Draw the straight line, then draw the zigzag to represent the thermal resistance. Then it goes draw a straight line, and then draw a dot, empty dot, to represent temperature T2 surface. And then it is labeled with thermal resistance and its calculation equation and heat rate with the arrow to represent the direction. Next, we will calculate the thermal resistance. We already have the equation. We write down the equation, then we plug into number natural log between R2 and R1, then 2 pi. This is the L, this is the K. So we get the thermal resistance. The last one is heat rate, which is defined as temperature difference over the thermal resistance. Then we plug into the number. We use the high temperature minus low temperature. This is supposed to be T2 minus T1. So make sure this always get a positive value, and then divided by thermal resistance to get heat rate value. For B, the spherical wall, students can do the practice on your own. Now we move on to example 3-2. We have a saying, there's a steam pipe passing through a large room at a temperature T surrounding 25. The pipe has diameter 70 millimeter, length over 1 meter, temperature of 200 degree, and emissivity of 0.8. It is exposed to cooler air at 25 degree with heat transfer coefficient H. We need to sketch the thermal circuit and find thermal resistance RT for convection heat loss from the surface. Where do we start? We identify the heat transfer mode. We have a temperature difference between solid surface and moving fluid. Then we have a convection. We have a temperature difference between a solid surface and a large surrounding, so that we have radiation. Then we can draw the thermal circuit. We start with high temperature Ts, go straight line, then zigzag, go straight line, then empty dot, label Ts, T infinity, RT convection, Q convection, and arrow to represent the flow direction. Next, we need to find the thermal resistance RT single prime. So we can go to the equation table. We're looking for RT prime. Then this is for radiation. Oh, this is for convection. That's the equation we're going to select. And go back. And this is the equation for RT single prime. Heat transfer coefficient. H is the pipe surface area, which is pi dl. and then this 2L cancel out, then it yields 1 over h pi d, plug into number h pi d, we get RT single prime thermal resistance for convection. Students will do the second question. See you next.